So the last reaction for alpha halogenation is called the haloform reaction. And this one used to be used a lot prior to NMR. It's a good way of checking for methyl ketones, and I'll show you why. So let's say that we have this ketone. This is a methyl ketone, meaning it has a methyl group coming off one of the sides, right? That methyl group over here has alpha protons, so I'm going to draw in the alpha protons coming off the methyl ketone. And just move this arrow right here. And in this reaction, you're going to use hydroxide as your base. And just like we saw yesterday, you can pop off an alpha proton because your conjugate base is resonance stabilized. The equilibrium is really not that favorable, though. So you don't make much of your enolate or enol. And in the next step of the haloform reaction, what you're going to do is treat this with some sort of halogen. So this halogen can be Br2, I2, or Cl2. And in lab, what you were using was bleach. Bleach is a really, really weak source of chlorine, right? Chlorine's a good oxidant. It's used to disinfect. It's used in laundry. And so when you show the mechanism, just show it as Cl2 and sodium hydroxide. The reason we didn't give you straight Cl2 to work with is it's a gas. It's really hazardous to work with, where bleach is relatively easy to work with. Most of you have it in your house. So in the next step, this will attack the halogen. You still have 2 more alpha protons left over. So I'm just going to show this as a generic halogen X. And just for the sake of time, you can repeat this twice. I'm just going to say times 2. So you deprotonate your remaining alpha protons and do the alpha halogenation again and again. All right, that gets us to this step. Where you have 3 halogens coming off of that alpha position. In the next reaction, you still have excess sodium hydroxide around. So the sodium hydroxide is now going to attack the carbonyl carbon and kick up electrons. Does anybody know why the hydroxide does it in this situation but not the other ones? Or at least not to an appreciable extent? Yeah, inductive effect, right? This is pulling a lot of electron density away from that carbonyl group. That means that carbonyl is way more electrophilic, and that hydroxide is going to definitely attack in. All right, so in this intermediate, we've got an oxygen with a negative charge. We've got hydroxide. And you've got your halogenated methyl group. Normally, we don't ever kick off carbons as a leaving group. However, in this case, we are. And why do you think this is an okay leaving group? Yeah, it's stabilized by the strong electron withdrawing force of those halogens, right? So in this next step, it's going to clamp down, eject off our leaving group. You end up making a carboxylic acid, and then this carbanion that you kicked off, that was our leaving group. Before anything can occur, this is really, really quickly going to steal its proton back from the carboxylic acid, so you can't really stop there. O minus plus HCX3. The neat thing is, if you use iodine in this reaction, this actually forms a solid precipitate in the solution, where your carboxylate will stay in solution because it's water soluble, right? Most carboxylate salts are water soluble. So if this precipitates out, that gives you a positive indication that you've got a methyl ketone. Prior to NMR, this was a really quick and simple way of determining if you had a methyl ketone. You didn't have to go out and hunt down equipment. However, you can do this with bromines and chlorines. The one we did in lab was with chlorine. So what you ended up making in lab was HCl3, or HCCl3. And so you ended up making chloroform in that reaction. Chloroform is really volatile. It evaporates out of the reaction, doesn't form a precipitate. All right. In the second step of the reaction in lab, if you remember, you had to adjust the pH to bring your carboxylate salt out of solution. Do you remember what reagent you used? It was aqueous acid, right? Because you want this to steal its proton back to give you your final carboxylic acid. And the carboxylic acid for our synthesis project wasn't soluble in water, and that helped us vacuum filter it, and it made our lives a lot easier than trying to extract it out of aqueous solution. Does that make sense? So it's a two-step reaction. The first step is with sodium hydroxide and elemental halogen. Second step's with HCl in order to precipitate out your product, or at least protonate it.
You got a carboxylic acid, like at the beginning. Why do you want to react it again?
Sorry, say that again? Are you saying why here?
Yeah, you're reacting it when you already have it.
Yeah, but the problem was in this step is when you kicked off this leaving group, it's so basic, it immediately steals that proton. You don't even have a chance to isolate your carboxylic acid because acid-base chemistry is the fastest chemistry there is, at least that we're aware of.
Did we use HCl then?
We used HCl for the second step of that reaction. So in your poster or paper, you are asked to show this whole mechanism. Like I said, just show it as Cl2. Don't worry about the overall bleach. It's in equilibrium, and the equilibrium is somewhat complicated. All right, so that's the last reaction for alpha halogenation. Now we get to start doing some interesting chemistry. We're going to start off with the aldol reaction. The aldol reaction is usually done with aldehydes. I'm just going to write usually an aldehyde. Oh. And in this reaction, you're going to treat this with sodium hydroxide, typically, and water. And when you do this, you end up coupling two of these aldehydes together. And forming a new bond. And this is referred to as a beta hydroxyaldehyde. Makes sense because we know we've got this alpha position and this beta position. We've got a hydroxy group coming off the beta position, and we're forming that new bond between the new alpha-beta position. It makes a lot of sense when you see the mechanism. So let's take a look at the mechanism. And just like we saw before, alpha protons are relatively acidic. So if you have hydroxide around, this hydroxide is going to pluck off one of these alpha protons. The equilibrium is not very favorable. So it's really going to favor the starting material side. However, you do end up forming a little bit of your enolate, and I'm not even going to bother drawing the hydrogens there. I'm just going to show the carbon with a negative charge. All right, and then if you have any unreacted starting material, which we know a lot of it is floating around, so I'm just going to write unenolized starting material. The enolate that you did form can attack the unenolized starting material that's just hanging around in solution. So it's going to attack in and kick up electron densities. One reason this really works well with aldehydes is aldehydes, like we saw previously, are really electrophilic, much more electrophilic than ketones, and so it works best if you have an aldehyde. And in this next reaction, or this next intermediate, excuse me, you're going to have an oxygen with a negative charge and your methyl group on there. And we still have water floating around in reaction. So the final step will be this stealing its proton back from water. So the hydroxide is catalytic for this reaction. Oops. Does that make sense? If you notice, though, I used equilibrium arrows. That means you can actually do the backwards reaction. So let's try to practice the backwards reaction. This is called a retroaldol. So in a retroaldol reaction, you're going to take that beta hydroxy ketone, or beta hydroxyaldehyde. You're going to react it with hydroxide and just do every step in reverse. So the last step we saw was protonation. That means the first step should be deprotonation. And then in your next step, this is the weird one. You can actually kick off a carbon. We typically don't see that very often, unless the carbon has some sort of stabilization. But in this case, it does, because the carbon we're kicking off is an enolate that is resonance stabilized. So we're splitting this in two, and we still have that water floating around. So if you have that water floating around, this can grab a proton back from water, give you your two aldehydes, which in this case we know are identical, plus your hydroxide. Typically, the forward reaction, the regular aldol, is favored. However, you can do this retroaldol reaction. It's an equilibrium condition, so usually it's about like a 70-30 mixture of the aldol product versus your original starting material. Does that make sense? So let's make some notes here. The aldol reaction is favored with aldehydes. The retro one is definitely going to occur if you try this with a ketone, though. It doesn't like to do an aldol with ketones. And then the other thing to remember is that this reaction is reversible. Does that make sense? Kind of basic reaction mechanism. The thing that used to always bug me when I was learning about this was this step right here where we kick off a carbon group. The main thing to remember is this is allowed because the carbon is resonance stabilized. So if you can kick off a carbon and it's stabilized through resonance or induction, it can occur. It's just not super favorable. Make sense?
These happen with like an ester attached or with
yeah, well, that's what we're going to see next. You're stealing my thunder. That's called the Aldol condensation. Yep.
Instead of the carbon getting brominated, can we do the just reverse salsa plus 5,000? Oh, never mind.
Okay. Let's do a practice one, and I'll show you some simple tricks for predicting products quickly. So let's say you're starting with this aldehyde. And you've got sodium hydroxide as your base, you've got water as your solvent, you've got equilibrium conditions occurring. What will your product be? 4 points. All right, let's try doing the mechanism together. So step one, we're going to grab one of these alpha protons and make our enolate. And I'm going to color code this, and you'll see why in a minute. It's helpful if you color code. That way you can keep track of your various pieces. But now we've got our enolate. And I'm going to have my unreacted starting material be a different color. So any unreacted starting material, we know that your enolate can attack into, pick up electrons to that oxygen. So let's keep track of everything with colors here. Oops, let me clean this up. We formed a new bond off the alpha position, so I'll show that as black. Over here, we've got a hydrogen and then an oxygen with the negative charge. That was our carbonyl carbon that's now attached. And that's our intermediate there, right? The number one mistake students make is they don't count their carbons and they lose them or gain them in the process. That's why I like double checking and color coding. All right, and then in the next step, what you're gonna do is react this with the water that's around. Kick this off as hydroxide. I'm not going to show the hydrogen anymore because we know it's there. Oops. And we've got our final product, which will be right here. One trick you can do is look at the alpha position next to your aldehyde, label that. The beta position must be the one containing the alcohol, right? Because we know we always form a beta hydroxyaldehyde. And then label the bonds that were made and broken. So this bond was made right here. And then this bond right here between the oxygen and that beta carbon, this used to be a CO bond. Does that make sense? I'll show you why this is helpful by putting you in the reverse situation. So this time, I'm not going to give you the starting material. You have to predict what the starting material would be. Again, 4 points. And for this one, product is going to look like this. And I want you to figure out what starting material must have been there. And like I said, identifying your alpha and beta positions can be really helpful. So let's identify our alpha and beta positions. So the alpha position, like I said, is always going to be the carbon adjacent to the carbonyl. So that's my alpha. The beta position is going to be the one with the hydroxy group coming off of it, like that. And we know we formed this bond, right? Because if we look up here, we formed that bond between alpha and beta up there. So going backwards, I could say this bond must not have existed before. I like drawing a squiggly line there. And then I can note this, and I can say this used to be a CO double bond, right? The hydroxy group is always the thing that was made from that CO double bond. So let's go ahead and draw our different pieces. So for example, that bottom half maybe look like that. I'm actually going to slide this over. And then the top half look like this one. They're two identical aldehydes, right? Which usually when you're doing an aldol, you'll commonly see two aldehydes. Otherwise, you get this huge hodgepodge of products that we'll talk about in a minute. Does that make sense? Sometimes, too, you can even color code it, too. So I've had students in the past just bring like a highlighter in, highlight this, and they'd say this fragment must have been that green fragment coming off there. And then the blue fragment, kind of like we did before, must have been this part right here. And you can use highlighters or colored markers to kind of help distinguish where each piece came from. That can be really helpful. Yep.
Do we look for identical aldehydes, or can we react to?
I'll show you how to work with a situation where you want non-identical starting materials. You can't use sodium hydroxide or else you run into a whole mess of products. Yeah. All right. There's a variation on the aldol called the Aldol condensation. The aldol condensation is a derivative of this. So, for example, we saw previously, that you could take sodium hydroxide and water and couple two aldehydes together to make your beta hydroxyaldehyde. The aldol condensation is where you take this and basically heat it up. And you make an alpha beta unsaturated aldehyde. And so what we'll do is we'll take a look at the full mechanism for this. And then we'll try to understand why heat favors this. So really quickly, we'll just practice our aldol. We've got these alpha protons right here. We've got hydroxide, which we know is a decent enough base to push this equilibrium at least a little bit forward. We end up making a trace amount of our enolate. That enolate can react with our unreacted aldehyde in solution, kick up electrons. You end up with your negative charge. And during this step, water can act as a proton donor. And like we saw before, you regenerate your hydroxide. So now the question is, how in the heck do we get to our final product? This is the weird part. So the next step involves another alpha proton. So we've got alpha protons right there. They're still relatively acidic, right? So in this step, it's going to grab one of these alpha protons and do something that resembles an E2 reaction, which is weird because I drilled into you first term that hydroxide is a terrible leaving group, but in this case, it is your leaving group, meaning I'm a liar sometimes.
Yeah, this is why because even cloning.
All right, so you end up making mostly this. This would be major. But if you remember from E2 reactions, you can get both an E and a Z alkene, meaning this will be your minor product. And why do you think that's minor? Sterics, right? Your alkene prefers to be kind of out of the way from that oxygen, so that's going to be your minor product. And then in addition, you generate hydroxide. Why do you think this is favorable under high heat conditions? It's a couple of reasons, right? So if we think back to elimination reactions in general, elimination reactions were favored under high temperature. Why is that? you get more moles of product, right? You favor disorder, right? In this case, we ejected off an oxygen, or a hydroxide, I should say, therefore increasing the entropy. We know increase in entropy is favored at high temperature. The other thing that's favorable is our product here is conjugated. Conjugated products tend to be more stable. So by increasing disorder, increasing conjugation, this is favored under high temperature conditions. Another reason, too, is because hydroxide is such a bad leaving group, you really have to crank on this to get it to go. It doesn't want to fall off very easy. So heat is an important consideration here. So let's make a few notes. Condensation is favored at high temps. I'm just going to write high T. Addition is favored at low or moderate temps. And like I said, condensation increases entropy and conjugation. Both favored at high T. Does that make sense? There are two very, very similar reactions. Condensation is just what occurs if you run it under high temperature conditions. Typically, it's still really only seen with aldehydes because in order to get to that aldol addition product, you really need an aldehyde for it to be favored. All right, so let's briefly make a summary because this does confuse students every year. Where if you have your aldehyde, and I'm just going to draw it twice to emphasize what's going on here. You can make your beta hydroxyaldehyde. And then if you take this with sodium hydroxide and heat, you can make your alpha beta unsaturated aldehyde. Like I said, this step is low or moderate T. However, if you desire to go there, just run it at high temp. Does that make sense? All right, so getting back to what somebody was mentioning earlier, what happens if you have two different aldehydes? That's called a crossed aldol. And for a crossed aldol reaction, let's say we've got one aldehyde. I'll make this one red. And then a second aldehyde. This aldehyde looks pretty similar, but instead of a methyl group, it's got an ethyl group coming off of it. How many products do you think we'll get if we mix these together with sodium hydroxide and water? Oh, it's tricky, right? So let's think about it this way. This one can react with itself and just ignore the blue molecule. And that's kind of what we've been seeing. So I'll show our new bonds being made and broken here. All right, so the red one reacted with itself to form a beta hydroxy aldehyde, excuse me. Or the blue one can react with itself. And if the blue one reacts, whoa. The blue one reacts with itself, it's pretty similar. you get your beta hydroxyaldehyde for the blue reaction. And then you can have the red one react with the blue one. So for example, what if the red one turns into an enolate and it does the attacking? But instead of attacking another red molecule, it attacks the blue molecule. If that's the case, you would end up with this product. Or you could have the blue one act as the enolate and attack a red molecule. So the problem with these crossed aldol reactions, like I said, is you run into a mixture of a lot of different products. I think what we're going to do is we're going to stop here. There's a trick to working around it. The main idea with this problem, though, is you're not exclusively forming one enolate over the other. However, there are ways around that where you can exclusively get one enolate. Order of addition matters a lot. All right, the other thing, too, is we didn't get nearly as far as I was dreaming about getting, so ignore your pod, hang on to it. It'll be due Tuesday.
Yes.
That is the best.